All right. All right. So what I can do today is if I need to use a whiteboard, I'll try to use my tablet as the whiteboard. So this part will be captured as well. And to do that, I need to run one little script before we proceed any further. And that script naturally has the name of fix stylus. There we go. All right. All right, so last time we were still talking about quantifiers. So this is where we left off on Monday. And I'm hoping all of you had a chance to read the material, at least finish this particular slide or module. And our last topic was how to filter so that the universal or the existential quantifier would only be applicable to a certain set that we are interested in. So that was kind of the discussion. So are there any questions from last time? No questions? All right. All right, so if there are no questions about that, we can now proceed. And oh, right, I forgot about one thing. Last time I said I would use like coding, like C++ code to try to illustrate the concept. So that's what I'm going to do now. I almost forgot about that. And that is in Joplin. Nope, that's not Joplin. Too many items here. So I might have closed Joplin already. Let me get back to the screen to start Joplin, which is all right. So this is the wrong class, I know, because we are in CISP440, and I'm going to create a new note for today. 20220831. All righty. All right, so go ahead.
You got a message saying you're still in the voice channel on Discord.
Oh, I forgot to get out of the voice connect from an earlier meeting. Thank you. Not that I'm talking about anything that no one should be able to hear because I got all the recording on YouTube anyway. But thank you. All right. So let me see, where's my cursor? There we go. All right, so what we'll do first is to kind of look at the C notation of a for all, okay? So if I want to say for all E in a particular set P of E, that's what I want to express. So in quote unquote C code, this is what I would do. I'm using plain C, so there's no Boolean type, that's just integer. So now we have a for all. And the first argument is going to be the set itself. So we are talking about set S over here. So I'm using some really kind of pseudo type here because there's no such type as a set in plain C. So I'm just using uppercase set as a imagined or imaginary type to indicate that S is a type, is a set. And then I'm going to use a predicate. And this notation is probably foreign to most of you, which is okay. So I'll explain that. So P in this case is a pointer to a function. So this is one way for you to pass a function to another function. So they can call the function that is being passed in to do a lot of things. You might have encountered this in QSort. How many people have learned how to do quicksort from one of your other classes? Okay, a few. Okay. So did you guys use the C library, the QSort library? No? Okay, because if you did, then you would have just encountered the concept of a pointer to a function. So here is what for all is going to do. I will have a local variable called result, and result is initialized to non-zero. So it's initialized to true to begin with. And then I'm basically making this up to there's no such thing as a for each in C and C++, but I'm just imagining that there is. And after that, I have an element that I call E. So E in S. There we go. So the idea of the for each construct is it's going to go through every element in S eventually. But the ordering cannot be determined because we know that ordering does not matter inside a set. Are we doing okay so far with this notation? Because I just want to see if you guys are comfortable with this. Okay. If you want to kind of look at the set as an array, I can do that too, but it's probably more accurate to do it this way. But the most important part here is result and P, and if you want to use the pointer thing here, that's fine too. So that is the key point here. It's a gigantic end. If you look at the for all quantifier, it really boils down to a gigantic end of P applied to each and every single element. So I'll give you another example in mathematical expression, so that way you can relate the code to that expression. And then when everything is done, result is returned. Return result. So that's kind of the equivalent code corresponding to for all. So in this case, what if the set S is empty? Can anyone tell me what it's going to return without even knowing what P is about? Okay, all we know is P returns a true false. That's all we know. But if you already know that set S as a parameter is empty, what is going to be returned? It's going to return true. Exactly. So that is important. And now I'm going to give you a mathematical one using the mathematical notation. So this time we say for all E in a particular set, and I'm going to spell out the values, elements in that particular set, and I'm going to use P of E here as well. So that notation, I'm just counting parentheses, is exactly the same as this notation here. It's basically P of A and P of B and P of C. So you can focus on just the right-hand side, because the left-hand side is how I use Markdown to type the notes. The right-hand side is actually what I want you guys to focus on. So is that okay so far? Now, if you look at the right-hand side, it does not seem like it's matching the logic on this side. Where's the true, right? Why would an empty set return a true? So let me modify that in just a little bit. So this way it's going to be clear. Because all I have to do is to say that. That's the initial true. That is also the default, of true. Is that making any sense? Now let's just kind of take out one element at a time to see if we can look at this and say, oh, okay, so now we know if you apply for all with a filter to its empty set, it's just going to be true. So I'm just going to do it step by step. If we take out C from the set, then it kind of makes sense that we don't have the and P of C anymore on the side where everything is spelled out. Does that make sense? Okay. So if I do this one more time and remove B, it's just going to be boring because you already know what's going to happen. Because and P of B is just going to go away when B is no longer in the set that I'm interested in. So if I do this one more time, then I would have made my point of what if the set itself is empty? Then we just have one left. without P of A. So that means if you are using a universal quantifier and you want to filter using an empty set, meaning that there's nothing of interest to you, the universally quantified statement, which is this thing here, is actually true. Now this is tricky because if you think about it mentally, it doesn't make sense, okay? Or at least at first glance, it does not make sense. But that is how the universal quantifier is defined. Do we have any questions so far about the universal quantifier seen from the perspective of just coding, and so everything is done sequentially? So good? Okay. So now we want to move on and talk about the existential quantifier. So since I'm really lazy, this is what I'm going to do. Copy and paste. And then we'll modify things as we need to. So now, instead of for all, we say exists E in S such that P of E is true. So now we just change the name of the subroutine, exists, and change the initialization to a false, and then change this to an OR. That is the existential quantifier. In other words, if you have an empty set, if S is empty as a parameter, then the default is going to return false. You have to find evidence that at least one element of S can make P of E true in order for the existentially quantified statement to be true. Are we doing okay so far? Okay. So I'm going to make some additional changes because all of these need to be changed as well. So now we have just exists, oops, and exists. And I'm going to do the even lazier thing here. This is not VI. I cannot do a search and replace not quickly. So let me just kind of scroll up here. But this time, instead of all the wedges, which are representing the AND, we have a 0 to begin with, because that's how we initialize result. So we have a bunch of zeros at the beginning. And then all the wedges, all the ANDs, become ORs. So we have OR, and so on. Oops. There we go. So let me just kind of show the part that is relevant to our current description. Are we good so far? I mean, are you guys kind of seeing the equivalency between the mathematical notation to the C code and also understanding, the default value of the two quantifiers that we have talked about so far? All right, very good. And if you guys want to, I can actually export this, to a file, or I can just give you the marked down file. So that way you can, download, install Joplin on your own, and then you can have the notes back. Yeah, okay, I can do that. But I cannot capture everything that you guys are thinking, so you still need to take notes, because, that part of your own thoughts, I cannot take note for you. Okay. Just remind me to release the note at the end of the class. All right. So I'm just looking at my squad here. Okay, everything is good. So the rest in section 4 is really just, translating or giving you the shorthand. So, I'm already using the shorthand because what this notation is shortened to this. I'm using the shorthand already. If I go back to my notes in Joplin, you can see I'm already using the shorthand of there exists E in a particular set, P of E, and also for all E in a certain set, P of E. So I have been using the shorthand already. All right. Any questions? No questions? All right. Are there any questions about the implication, what the implication is doing inside the statement, why this particular thing is going to filter, and we only pay attention, in the end, we really only pay attention to elements of X. Everything that is not an element of X is not influencing, the outcome of the universally quantified statement. We talked about that on Monday. I just want to double check to make sure that we are clear on that one. So we good? All right. So that means we are done with this particular module. And we can now go back and revisit the set notations, but this time we'll be seeing those from the perspective of quantified statements. So we'll see. We'll go back to set theory. It's more like your set notations, not really theory, using quantifiers. So the rationale is, before we tried to explain things without using quantifiers by re-examining those notations, but this time we try to use quantifiers. I'm just trying to help to reinforce the concept of the quantifiers. So we'll look at equality first. Given two items, x and y, so there are two values, x and y, how do we know they are the same? In other words, how do we evaluate x equals to y, which has to evaluate to either true, yes, they are indeed the same thing, or false, they are not the same thing. First of all, if one is a set and the other one is not a set, then we have a type incompatibility. That makes x equals to y false automatically. In other words, we have a type mismatch. Okay, if they don't have the same type, they cannot be the same. Okay, so that's an easy one. Given that x and y are not sets, then the normal comparison applies. So if one is an integer of 5, the other one is an integer of 4, obviously they're not the same. So the only tricky one is what if they are both sets? So if x and y are both sets, then we can say x equals to y if and only if everything in x is also in y and everything in y is also in x. Now, the bigger question is, why do we need this and here? And why do we need both of these expressions? What if we only have one but not the other one? So imagine this. Imagine that we only have the left-hand side of the and, but not the right-hand side. Forget about this part here. We only have this part here. All it is saying is everything in x as a set has to be in y as well. But then y can contain extra elements. And if y contains extra elements that cannot be found in x, I don't think we should call x and y the same, because they have different membership. One has more thing than the other one. So vice versa for the other side. So the right-hand side handles the other case where everything in y is also in x. But now, this time x can have extra things. It will still make this particular statement true. So in order for two sets to be the same, we need both of these conditions to be true. The other way we can say this is x equals to y if and only if for all e, everything in the entire universe, okay? So we are no longer just limiting to x and y. But if you look at everything in the universe, just take out one thing in the entire universe. E is an element of x if and only if E is an element of y. That also works. Because this if and only if means if this thing is not in x, it better not in y. If it is in x, it better in y. If it is in y, it better be in x. If it's not in y, it better not be in x. So it goes both ways. Are we doing okay so far at this point, with section 3, which talks about, how do we compare two sets? Okay, all right. So set description, we call the notation E equals to x such that P of x is true. So now we can use a universal quantifier and basically re-express this statement here to be the same as this. For everything in the entire universe, if x is in E, x is in E if and only if P of x is true. Because P of x is the membership function to determine whether x is supposed to be in E or not. So let me ask you this question. What if I change this if and only if into a just one arrow going this way? In other words, I turn the if and only if into a if. If x is in E, then P of x is true. So why would that not be desirable? I'm turning the if and only if into just if.
You can let in untrue values.
So in order for the, okay, I think you're definitely on the right track. Because if I turn the if and only if into an if, in order for the implication to be true, there are three ways to make it true. False, false makes it true, but that's what we want, okay? True, true will make it true, which is also what we want, but there's an extra one, which is false, true. That will also make the implication true. So that means we can miss certain things in the set E where that thing also makes P of x true. So we'll be missing elements. We can potentially be missing elements if the if and only if is just a simple implication. What about the other way around? What if I turn the if and only if into only if, which looks like an implication, except it only goes to the left-hand side? Then it becomes the opposite problem. We can now contain extra elements in E where those elements would make the predicate P false. So we can contain extra elements in that case. So this is why if and only if is really essential, because without the if and only if, even though it sounds about right, it's not. Are we still doing okay so far? All right. So a lot of the terminology, but a lot of these terminology would actually be useful and critical in the later discussions in this class. So that's why I really want to emphasize why it is important to use an if and only if in this case. What about the empty set? How do we describe the empty set? We can say, it is not the case that there exists an element in the entire universe such that X is an element of S. So that's one way to describe or to qualify that S is an empty set. It's just a long way to say, the same thing, open curly brace, close curly brace. And then we have intersection and union. This is intersection. So to express intersection, we can now say for everything in the entire universe, that thing, pick one thing, okay? Pick one thing at a time. That one thing is an element of the intersection of A intersecting with B, if and only if that thing is found in A as well as found in B. Which is really close to what we said, before, except this time it is universally quantified. Same thing with union, except the and becomes an or. And then for Cartesian product, it's kind of the same thing, except this time we have a nested quantified statement. So we have for all x in A as the outer quantification, and then we have for all y in B as the inner quantification. So now we have a nested. It's kind of like a nested loop, where the outer loop goes through everything in A, the inner loop goes through everything in B for each item in A. So can you guys kind of imagine that in your head, with two loops? The outer loop deals with everything in A, and then the inner loop deals with everything in B. So then we basically say xy as a two tuple is in the set of A Cartesian product with B, and for all A xy in A times B, it is kind of the same thing. So this and is splitting between this side, which is the entire left-hand side, from this side, which is the entire right-hand side. Are we doing okay so far with this? What if I don't have the and? What if I just focus on the left-hand side without the right-hand side of the overall and. What might happen in that case? So without the and, I'm still saying, for pick something in A, pick something in B, that one thing from A and that one thing in B, we use it to make a two tuple, and then we make sure that that is in the Cartesian product of A and B, which means we'll get the right membership. But it doesn't prevent us from having extra elements. It does not help us restrict the Cartesian product from having extra elements that are not in the form of xy, where x is coming from A and y is coming from B. That is the reason why we need a conjunction here. So the other side of the conjunction says, everything in A has in A type 8, the Cartesian product of A and B is in the form of xy. And the restriction is x has to come from A and B has to come from Y. So this way, the two basically, one handles the case of we have to make sure that we contain everything that we're supposed to contain, but it doesn't. It allows extra things to be in the Cartesian product. The other one, make sure that we don't have anything extra in the Cartesian product definition of A and B. So the two together make sure that we have exactly just the right elements in the Cartesian product. And then last, we have the subsets. People in the back may have some difficulty reading this one. So A is a subset of B if and only if everything is in A is also in B. We saw that earlier. And then the other one is A is a proper subset of B if and only if A is a subset of B already, and there exists at least one element in B such that that element is not in A. Basically the same thing that we worked with before, except this time we are properly quantifying all the statements. All right. So are we okay so far? Because this is the end of all the set notations. From here on, we're going to use these notations in order to express other things. So we all good? All right. So if we are all good here, then you have an assignment. You have a homework assignment. And the homework assignment it's just called set theory. I will open it up, and I'll give you 1 week to work on it. And I have to make sure the answers are shuffled. Last time I forgot to do it, and then people notice, hey, the first answer is always the right one in all the multiple choice questions. So I got to remember to do that. And the due date is 1 week from today. And that will make it the 7th of September. And I will make it due at the beginning of this class, so it's going to be 3 p.m. So September 7th, 3 p.m. Save and publish. There we go. So you now have one homework assignment. You might want to write it down. Canvas does keep track of your assignment pretty well. I mean, if you just sign in, you know that you have assignments due in a week. So after this, we are now moving on. So I'm going to take roll later on today, and that's why I asked you guys to kind of sign in, make sure that you have access to Canvas at this point. So the next topic is functions. So I'm going to go open this one up. And the way functions are defined is we're going to use set of tuples to do it. So the first part is talking about tuples. We kind of talk about tuples already, but it doesn't hurt to talk about it again. So a tuple in general is an ordered container where its components are ordered, and the ordering is significant. So I'm just reading this sentence here. And then the second sentence reads, a tuple can contain duplicated items. Okay, this is the second one. And then the third one is just an example of the tuple of 1, 1, 2 is different from the tuple of 1, 2, 1 because even though they all have 3 elements and the same value exists in both tuples, the ordering are different. So for the most part, we can think of tuples as arrays, because an array containing the first element being 1, the second element being 1, the third element being 2, is probably considered different compared to an array of 1, 2, and 1. So that's how you can relate tuples to a concept that you have learned in the past. It's really just a fancy name for an array. So the way we write a tuple is already, we got plenty of examples already at this point. A tuple is represented by a comma-separated list of items enclosed in parentheses. So this time we are using the usual parentheses as the delimiters of a tuple. Because of the concept of a tuple is similar to the concept of an array, we borrow notations from array operations. So given that T is a tuple, we use T bracket I to specify the ith item of the tuple. So nothing new here. And just like in most programming classes, we start with index 0 and not index 1. So the first item is square bracket 0, not square bracket 1. So are we good so far? Basically, all this is saying is we are equating tuple as an array in C, C++. And then bar T bar specifies the number of items in the tuple, which is otherwise known as the length of an array. So are we good so far with what a tuple is? A tuple is an array. We can figure out how many items are in the tuple, and we can also designate a particular item in a tuple using the square bracket notation. Same stuff that you have learned in arrays already. So now we get into functions. So we learn functions in other math contexts. Because all of you have taken at least pre-calculus, you already know what a function is. F of x equals to x squared plus 4x plus 2. That's a function. Okay, you just plug in the value of x, and you can calculate the value, over and over again. So, but the way we look at functions in this case, in this class, is a little bit different. So first of all, there's this notation. What this notation is saying is f is a function where x as a set is the domain and the y as a set is what we call the codomain. Some of you may have learned the term range, okay, when you're in your calculus or pre-calculus class. It's the same thing, okay? So range in your other classes in the context of a function is what I call a codomain in this class. So just a little terminology, equivalence here. And this arrow here, all it is saying is to make sure that we can differentiate what is the domain and what is the codomain. I did not invent this notation, so you will see this notation actually being used in many other types of documents that would describe, functions. So now we have a particular example. So we have a normal way of defining a function of f of x equals to 2x. Okay. So now the question is, if we confine x, the domain, to be the set of all integers, then we can also use the set of all integers as the codomain. So as a result, we can now describe f as a map from the set of integers to the set of integers. Is that making sense so far? But somebody is going to immediately point out and go, oh, but some of the things in the codomain are not mapped to. Because we have 0 mapped to 0, 1 mapped to 2, 2 mapped to 4, 3 mapped to 6, and so on. So who's mapping to 1? Who's mapping to 3? The answer is nothing. You don't have to use up everything in the codomain, and it will still be a function. All right? So if we want to enumerate what is in F as a set, so this is new to probably all of you, is to look at the function as a set of 2 tuples. So if we are to look at this particular function as a 2 tuple, these would be the elements or some of the elements in that particular set. Because we say 0 is mapped to 0, 1 maps to 2, 2 maps to 4, 3 maps to 6, Of course, on the negative side, we have -1 mapped to -2, -2 mapped to -4, and so on. In fact, we can also use this notation here. You're going back to the notation where I don't have to list everything. So this notation says your F is a set because we see the curly braces where each item, each element looks like x comma 2x, x and the double value making a 2 tuple. But it also has a restriction. X has to be in the set of integers. So that's another way to specify what is the membership of the set F. But F is a function. So in this class, when we talk about a function, we are talking about a set of tuples. And that obviously translates to this one, which is saying, for every x in the set of integers, for every element in y in the set of integers, y equals to 2x if and only if xy is an element of F. So when we use the two universal quantifiers, by the time we get to this particular open parenthesis, by the time we get to here, it is entirely possible that x is 1 and y is 20. So then you're going to say, oh, but in that case, 120 cannot be in the function. That's right. That's exactly what it's saying. Because 20 equals to 2 times 1 is false. Right? If one side is false, this is an if and only if. The other side has to be false too. So that makes sure that 1 comma 20 as a 2 tuple is not in F. So this is a very long and clumsy way to say something like this. Do we have any questions? So these are just examples, okay, just so that we can get started to start to understand that we are now looking at functions. A function is a set where each element is a 2 tuple, and the first item of the 2 tuple comes from the domain. The second item of the 2 tuple comes from the codomain, otherwise known as the range of the function. So the next question in section 3.1 is asking, what makes a function a function? I really should change this, what makes a set a function? Okay? But just to make it catchy, I said, what makes a function a function? So the first thing we need to know is a function is a subset of the domain Cartesian product with the codomain. Is that okay? Does that make sense to you? No? Okay. Now this is just restricting that F has to be a subset. It doesn't say anything about the other properties of a function. Okay. So let me give you an example. So we are going to use the same example as in the text. So F is a function that maps from integers somehow to the set of integers also. Okay. So when you see this notation, you know that the domain is made out of integers. You also know that the range is made out of integers. But the exact mapping is not set. There's nothing here that will say, oh, we are mapping this integer to that integer specifically. All it is saying is, well, we are mapping integers to integers. That's all it's saying. Is it possible to map every single integer to one single integer like 0? Yeah, totally possible. Because I'm not telling you how things are mapped. Are we good so far? All right. But would that set be a subset of the Cartesian product between integers and integers? It is, okay? That is why we have the restriction that I have stated here. So if X is the domain, Y is the codomain. If F is is a function, then f has to be a subset of the Cartesian product between x and y. In other words, a function is a subset of the Cartesian product between its domain and its codomain. It's a very simple restriction, doesn't tell us much about how things are mapped. In fact, it is just the first requirement. This is a necessary condition for f to be a function. It is not a sufficient condition for f to be a function. So this is one of many requirements in order for f to be qualified as a function. So now we move on to the other part. So in addition to this observation, f has to be a subset of the Cartesian product. There's another criterion for a subset of x Cartesian product with y to be a function. In English term, each element of the domain must map to one and only one element in the codomain. So I'm going to highlight the sentence here, because what we want to do is to find a way to express it not in English, but using the terminology that we have already introduced. So how do we do that? How do we get started? Each element of the domain must be mapped to one and only one element in the codomain. So the entire rationale, the entire reasoning of how I came up with the final notation is explained here. You are more than encouraged to read all the intermediate steps before I got to the final answer, because I did not copy this from a textbook. This is actually my reasoning, how to go from here, which is what I want to express, to the point where I can use the quantifiers and the other set notations to express that thing. Okay. Does everybody understand what this statement means? Each element of the domain must map to one and only one element in the codomain. What does that mean? Well, let me give you some examples, and you tell me whether in those cases whether a set is a function or not. Okay, so I'll give you a few examples. So you might want to keep this part up, on your browser or on your mobile device, whatever you're using, because you might need to refer to it. Oh, okay, I'm just going to copy and paste it to the other side, so you don't have to flip-flop between two screens. So I'll just kind of copy and paste it here, and then I'll give you some examples. I'm going to give you some assumptions first. The domain is ABC, and then the codomain is 1, 2, and 3. So I'm already telling you, what is my domain and what is my codomain, but I want you to tell me whether the following sets are functions or not. Okay? We'll start with something simple. We'll start with something like this. We have A1, B2, and C3. Would that be a function? Once again, you guys can focus on the right-hand side. Forget about how I actually type it in Markdown. So would this be a function? Does it meet the requirement that every element in the domain is mapped to one and only one element in the codomain? This one is quite obvious, right? Have we covered everything in the domain? Yes. A is mapped to A. A is mapped to 1, B is mapped to 2, and C is mapped to 3. Okay, so the first requirement of every element in the codomain is mapped. Second one, is each one mapped to one and only one element in the codomain? Yeah, I think we met that requirement too. A is only mapped to 1, B is only mapped to 2, and C is only mapped to 3. So all the requirements are met in this case. So now we say, yeah, we can see this as a function, is a function. Now, obviously, when I say is a function, it is in the context of what we have chosen as the domain and what we have chosen as the codomain. So you always have to keep in mind when I tell you, oh, by the way, this particular set is a function, you always want to ask a follow-up question of what is the domain and what is the codomain. All right, so if this one is easy, let's try something that is not as obvious, but still pretty easy. So we'll have A1, B1, and C1. Would that be a function? Does it still meet all the requirements of each element of the domain must be mapped to one and only one element in the codomain? It is still meeting that requirement. But then if somebody is asking, at least in mentally, but they're all mapped to the same thing. Yes, so what? The question is one an element in the codomain? Well, then it has met the requirement. It did not say anything about uniqueness. It did not mention anything about each element of the domain must be mapped to one unique element in the codomain. There's no uniqueness requirement in this case. All right, so let's move on. And then we'll ask this one. And this one will have A1, A2, and then we have B1 and C3. So the question is this a function? If it is a function, then we have nothing else to say. If it is not a function, why is it not a function? Which rule did it break? So first of all, is it a function? Well, because of the way I asked the question, it probably is not. So now the secondary question is, why is it not a function? What would be the explanation based on the requirement itself? Which rule did it break? Yes?
The fact that the domain is mapped to, or the domain is mapped to elements in the codomain.
It broke the rule of one and only one. Because A is an element from the domain, but it is mapped to two elements in the codomain. So it broke the rule of one and only one, because in this case, the cardinality or the count of codomain elements mapped from A is 2 instead of 1. Okay? All right, so let's move on to another one then. So this time we have B1 and C3. And that's it. So is that a function? It is? Is it a function? Which rule did it break? It actually broke two rules at the same time, but we can call that one. I think you got your hand first.
Each element.
All right, so each element is broken because A is not mapped to anything, but the requirement here says every element, each element of the domain must be mapped blah, 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 blah. Okay, I don't even care about one and only one at this point because I need every single element in the domain to map to stuff, right? 1, 2, or 3, I don't even care about the one and only one. The fact that A something does not appear anywhere within this set means it had broken the rule of every element of the domain, blah, 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 blah. Okay? But it also implicitly broke the second rule because you can also say that A is mapped to nothing. So if you're counting the number of things in the codomain that A is mapping to, it is 0. Do you think 0 meets the requirement of one and only one? The answer is no. But that brings me back, I forgot to mention one thing. Why do I choose to use the phrase one and only one instead of just one?
It's kind of like an if statement.
Sorry?
It's kind of like an if statement.
It's kind of like an if statement because if I just mention one, there's an ambiguity. And what is the ambiguity if I chose to say map to one instead of one and only one?
You can get situations like in the third row where you have A1, A2, B1. Like sure, A has no. It's more like A1, B1, C1.
Because
they map, like A can have multiple different things because it's just matching to one.
Exactly. Yeah. Because when I say if I change the phrase to map to one element in the domain, this would have met the requirement. Because when we use one, it is implied it is just at least one. But if I say if one and only one, then it's not at least, because it is exactly one. So I could have changed the phrase to not one and only one, but exactly one. That would have meant, that would have been clear as well. Are we good so far? Are you guys convinced that reading notes for this class and also exam questions in this class may be slightly different compared to reading a novel like, Lord of the Rings and so on? Because every word is important. Okay? All right, let's move on. So I think we got the concept, okay? We got the concept. The next question is going back, and we are asking the question of how do we express this without using English? And we boil everything down to the symbols that we have defined up to this point. But before we go there, why do I want to do that? Why do I want to use mathematical symbols whenever I can? What is special about math symbols? What is special about programs? Why don't we program, in natural language?
They can be used in multiple areas, like they can be universal.
It can be, so if I understand correctly, you're basically, so different people may look at the same sentence and interpret it differently. Interpret it the same.
Math, right? So math can be interpreted the same by multiple people.
Oh, in math symbol, which means, if we do not use mathematical symbols, then we can potentially have confusion because things can be ambiguous. So that's exactly why. Before I move on to any further, I can see you guys are kind of bored already. So I'm going to bore you a little bit more with some stories from my graduate school. So in my graduate school, my dissertation was one single proof of something. It was just one huge, gigantic, long proof. And I was using mathematical symbols the entire way, because I thought the same way as I do now, and think, hey, if I use mathematical symbols, there's no ambiguation, and I think the professors of my committee would be happy about it. Well, that turned out to be not true, because we are not talking about math professors, we are talking about computer science professors. So my professors looked at my dissertation, or the draft of my dissertation, which was only, I think, about 60 pages, which is super short for a dissertation, a PhD dissertation. My professors came back to me and said, "Tak, you have to use English." And then I go like, well, I mean, okay, I can put in some explanation here and there. Then where am I supposed to put all these mathematical derivations? You can put it all in the appendix. I go like, but that means like 80% of my dissertation is in the appendix. So that's one thing that's funny about my dissertation. The second thing is also important, especially in this class. At the beginning of writing my dissertation, my advisor just told me, okay, so you can use this theorem as a starting point of your dissertation. And it was seemed to be a pretty useful theorem because it helps me to limit a lot of cases. So for the first 2 weeks, I worked with my dissertation and started to do derivations and whatnot. I go like, and then in week 3, I thought about this and I go like, okay, something is gnawing at me. That's the best description that I can give you is it's gnawing at me. Remember what I told you about my superpowers? Did I tell you about my superpowers? I know when I don't understand something, right? And this is my other superpower, which is kind of like a derivation of the first one, is if something doesn't add up, I get a gut feeling about it. Call it the spider sense, okay? It's the spider sense in a very limited context. So I got this tingling spider sense, and then I went back to my advisor and I told him, okay, are we really sure about this theorem? My advisor said, yeah, it's in so-and-so's master's thesis. It's already proven, okay? So you don't have to waste your time to try to prove this one. I go like, whose master's thesis contained this proof? And he told me about it. So I went to the library, checked out the master's thesis that was done maybe a year ago. It was really recent at the time. And there was no proof, okay? The only mentioning of that theorem was, obviously, blah, 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 blah. That was it. I go like, okay, that's not a proof. Okay, I do not see derivations. I do not see the steps. It wasn't convincing me. So I went back to my advisor, who is basically saying, Tech, why are you wasting your time? So I thought, okay, give me 1 week. If I can't, prove that the theorem is one way or the other, either right or wrong, then I'll just go ahead and assume it is true. So in that 1 week, I found a counterexample. I constructed a counterexample case to prove the theorem was wrong. Now, that was at the very beginning of my process, so I didn't waste a whole lot of time, maybe 2 or 3 weeks, no big deal. I went back to the lab and I told my lab mate about this. He was almost done with his own master's thesis based on, guess what? The same quote unquote theorem. I have to say quote unquote because it's not true. And he just blew up. Fortunately, he still retained enough rationality to not to blow up on me, and he was just basically blowing up on my advisor. So that is my lesson to you of why it is important to use precise language whenever it's possible, and two, don't take anything for granted. Okay, if somebody, especially when someone says obviously, which you'll see a lot in your near future. When you're moving on to a 4-year university, there will be a lot of textbooks that uses obviously blah blah blah. So when you see that kind of sentence in a textbook, what are you gonna do? Check it, because every time you check something that was quote unquote obviously, I mean, most likely than not, okay, unlike in my situation, that theorem is probably true. But it doesn't hurt to try to prove the theorem yourself, because every time you do something like that, you're only helping yourself to gain a better understanding of what you're studying, and you're practicing your proving your skills of doing mathematical proofs. So that's just that's my take on it. Okay, if someone says but I don't want to do anything like that, hey, that is your choice. Okay, it's fine too. All right. So getting back to where we are now. So eventually I derived and derived and derived, and this is, let me see, is that the one? Yep. So this is the final form of, in addition to um, f being a subset of the Cartesian product of x and y, this is the additional condition in order for a function to be a function. So I know, especially for those of you who did not, read ahead of me, so this is new to you. You look at this and go like, whoa, this is way too much. Okay, well, what do we do? What do we do when we encounter, something like this, where, yeah, I think we have talked about each and every symbol or notation on its own, but we really haven't talked about, how things like this are put together. What would be your first response?
Break it apart, bring my bit.
Exactly. Instead of running like a chicken without its head, which is a natural reaction. I have to admit it is a very natural reaction when people see a notation or a complex expression of things that you are not familiar with. Well, you don't become familiar with something by running around like a chicken without its head, right? We become familiar with something by exploring and working with it. So that's what we'll do. So we have a universal quantifier here, which basically says, let's go ahead and evaluate this thing here for every single element of x. And we have to make sure that this portion is true no matter which element we pick from x. That's what the outermost expression is trying to say. Are we good with that? Okay? So now we know where E is coming from. E is just a element from x. But this better be true for no matter what we choose from x. Okay. So now we get into the inside part here, and now we go like, okay, what is that saying? Well, if you look at the outermost operator, it is the cardinality operator, which is basically saying, what is the number of elements in the set inside, right? It's just asking about the number of elements. Okay, that's not too hard. And comparing the number of elements of a set to 1, I think that's okay, because the number of elements of a set has to be a natural number. It may be 0, maybe 1, maybe 2, but it's a natural number. I want to compare a natural number to another natural number. Okay, that's fine, not a problem. So now the question becomes, what is the set that we're dealing with here? So the set that we're dealing with here is, from here to here. And this is the notation where we can say every element in this set, if it has any element is going to be in this form of EQ. So E is already known, it has to be something from X. Q is like floating, it's like, okay, this is just a format, okay? It's a wildcard format to say every element in the set is in the form of E, comma Q as a two tuple, but there's one extra requirement. It has to be an element of F. So that means, okay, let's go back and apply this to one of the examples that we have earlier. In fact, let's apply to all the examples that we have earlier. So let me do this part first. Copy and paste in Joplin. So this is the other reason why Joplin is cool, is because I can do something like this. Oh, I thought I copied, but maybe I did not. Let's do that one more time. Show math as, tech command, copy the clipboard. I should not have to select first, but I could be wrong. Okay, paste. There we go. Excellent. Okay. So now we are going to evaluate this, and we'll evaluate it for every single E. So we say, what if E equals to A? Okay. In other words, if you focus on the right-hand side, we are dealing with this as a function as F. So let me just add F equals 2 to make it very clear what we are trying to evaluate. So we look at this one here. Oh, I'm trying to edit on the wrong side. And then we say F equals to that. All right, so now we have to evaluate what happens when E equals to A. I will just say, is it true or false? If E equals to A, what is the set where we're looking for two tuples of F where it starts with A as an element? We got A1, right? And what would be the cardinality of that? So let me just type the entire thing out, so this way it's clear what we are talking about. So we are looking at the cardinality of a set where A1 is the only element, because that's the only element in F that meets the requirement of starting with A, ending with something else. And then this is the cardinality. This equals to 1 is true. Once again, you guys can focus on the right-hand side. Are we good so far? By applying, not the universal quantifier, but what is inside the quantifier, assuming E is A, that met the requirement. But that alone is not enough, because we have to say for all. So now we have to say, what if E equals to B? But you already know the answer to that question, because this is an easy one. So now we go like, okay, I'm just going to be really quick here. So B is mapped to 2, so we got B to here, but the cardinality is still 1, okay, not a problem. And then what if E equals to C? C is mapped to 3 in F, and the cardinality of a set consisting only of the two tuple of C3 is also 1. So now we have just shown that for every single element of the domain, because we make the assumption of the domain here, the condition that we want to evaluate is true, true, and also true. Woohoo! That means this F here is indeed a function. Are we good so far? Are we clear? How I am step by step applying the universal, the quantified statement to F as a potential function. Okay. So we'll go ahead and apply this to something that is not a function, because that's actually what makes it fun, is when something is wrong, like the theorem related to my dissertation. And someone may say that I have a twisted sense of what is fun. All right, so now I am going to look at this function definition and apply, oh, you cannot see the entire thing. Let me scroll up. There we go. And I'm going to put a blank line here because otherwise it doesn't know that we are opening a new paragraph. That's the problem. Right, so just formatting stuff. There we go. All right, so now we are evaluating this one, and we have to change it because this time it's an empty set. When E equals to A, and I want to compute, how many things in function f is mapping to something in the codomain, there's nothing. What is the cardinality of an empty set? Yep. It's 0. That means 0 equals to 1 is false. Is that okay? Yep. Of course, this one has B1 instead of B2, so just to make it correct, I have to fix that. Excuse me. Okay, but we have two sets that are not functions. This is one of them. The other one is the one that has 4 elements. So let's work with that one too, because I just want to make sure that you guys are kind of understanding how we apply the universally quantified statement to see if something is a function or not. So now, how many things in f, okay, let me see what if f is. So how many things if in f maps to something in from A? So there are 2 things, right? Because we got A1, we also have A2. The cardinality of this set is what? The cardinality of this set is 2. 2 equals to 1 is false. Woohoo! Okay, so we got 1 false, and then the other 2 would be a B1 and a C3. Those 2 would be 1s, but we need everything to be true. Why do we need everything to be true? Why do we need this to be true for f to be a function? Because it was what kind of a quantifier do we have? Every, which is a universal quantifier. So if it fails on one of the many elements, it's already failing. Are we good so far? All right. So on one hand, someone can say, this is really an obscure way to describe that each element of the domain has to map to one and only one element in the codomain. At the same time, it doesn't leave any ambiguity. Is that okay? All right. So why is the concept of a function useful? Well, in this class, we are not dealing with functions that you're normally encountering. In pre-calculus, in algebra, you're dealing with functions like sine, cosine, exponent, log. They all have uses, okay? In everyday life, they have a lot of uses. So in this class, we use functions in a very different way. So the kind of functions that we deal with, some people will even say, oh, that's really arbitrary, okay? Because why would you map this to that and map that to that and so on and so forth? So before I answer that question, let me ask you this question. I'm not sure which class taught sorting. Was it 360 or 400 or 430?
I think 360.
360? Okay. So if your professor is trying to describe a sorted array, given an input array and want to describe a sorted array, what do you think would be a good description of a sorted array? So I'm going to give you some alternatives here. In other words, if I am a professor in CISP 360 and I want to use mathematical symbols to describe what a sorted array means. So let's go ahead and see what works here. Okay, so we assume the input array is, okay, just for the lack of a imagination, it is A. Okay, A is an array. What qualifies the output as sorted? So whether you want to make it an in place or not in place doesn't matter, but we'll just assume it is an in place sorting algorithm. So using there we go. Okay. So this is what this is what the professor wants to express. But using mathematical symbols, how would you describe that? I'll let you guys think about it a little bit when I drink some water. It's okay to start with the simplest way you can think of, and then we'll try to find out what's wrong with it and how to refine it. So we'll start with something that seems obvious, okay, which is the exit condition of the algorithm is, and now we use mathematical symbols. A bracket 0 is less than, okay, let me close that first, less than A bracket 1 is less than, well, less than or equal to, okay. Something like that, okay? Well, that seems to be pretty normal. I mean, especially if we can have duplicate values in the array, right? I mean, sounds pretty reasonable. We want A bracket 0, the first element, to be less than or equal to the second element, which is then less than or equal to the third element. And then the last element has this kind of weird format, but that's because we talked about cardinality already. So bar A bar is the length of the array, and the index of the last element of an array is the number of items in the array minus 1, because we used up 0 to point to the first item in the array. Well, that seems to be reasonable. But in that case, I can write an algorithm that's really easy and it will get the job done. Okay? So the way the corresponding algorithm that I would write is going to look like this. So we'll say void sort, and let's just say each element is an integer. So A is pointed to an integer, and in C and C++, there's no way to actually know the length of an array. So I would have to pass that in as an extra parameter n. Does everybody understand what I just said? There's no way for me to tell how many elements are in an array, because in C and C++, an array is basically the same thing as a pointer. There's no way to tell how many items there are in the array. So n is really bar A bar, okay? So I'm going to comment here and say n is really the same thing as bar A bar. All right, so this is my algorithm. My algorithm is going to use unsigned I as an index variable, and I say for I equals to 0, I is less than n plus I, and I just have to say A bracket I equals to 0. Then I turn in this algorithm, and then the professor is going to say, Attack, this is not even close. This is not even close to sorting. And I go like, well, according to your description, it meets all the requirements, right? Do you guys agree that this algorithm meets the requirement of A bracket 0 is less than or equal to A bracket 1, which is less than or equal to A bracket 2, and so on? Because they're all zeros. Of course, they're all less than or equal to each other. What is missing? How can, sorry, go ahead.
They have to be within the set.
It has to be within the set. Okay, very good. So now how do we express that? In other words, if you have one, everything has to be accounted for, right? So if the original array, if A was, okay, let me scroll up so you can see it. So if A was, before it is sorted, if it is 4, 3, 3, 4, when it's done, we want A to be 3, 3, 4, 4 is the right answer. But we don't want it to be 3, 4, 4, 4. That would not be the right answer. Because even though I got all the right values, the count is different, right? So that would be wrong, is wrong. And then 3, 3, 3, 4 is also wrong. So now the question is, how can we specify something like that?
If the sets are equal, if the sets are equal, like
Well, it won't work because remember, a set, it won't be able to count how many items. What is the count of each thing? So if you because this works in an array, but you cannot turn this into a set. Because in a set, you cannot say 3, 3, 3, 4. There's only 1 3 and 1 4. So what can we do? So what we do is something like this. Okay, so we're getting closer to the explanation of why we look at functions the way we do in this class. So I'm going to say this, okay? So first of all, this notation really sucks because it's just saying like, okay, so I have to kind of imagine what the dot dot dots are representing. It's not very clear exactly what it is. So the first requirement is going to be something like this. Okay, fine, we'll go ahead and repeat this, but this time I'm going to use a universal quantifier. So I'm going to say for all, and this time I use I in, there are several ways to put this. So I can say for all I in math BBN, and that would be the set of all natural numbers. And then the statement that I need to quantify here is if 0 is less than or equal to I, which is less than bar a bar, then, okay, right arrow, then we want to make sure the following is true. We want to make sure that, oh, I forgot one thing. There's a -1 here. Then we want to make sure that a bracket I is less than a bracket I plus 1. That would be the first requirement, which is capturing exactly what I had earlier, except this time I'm using a much more precise language to say where does I start, where does it end, and for each value of I, what am I trying to look for? Is that okay? So why do we need this implication thing here? The implication is here as a filter. Because if I is greater than bar a bar -1, I don't care because it's out of bound already. If it is out of bound, then the left-hand side of the implication is false, which means the implication itself is true. So it won't cause a problem with the overall universally quantified statement. So that's a filtering mechanism. And I made a mistake again because this is supposed to be bar a bar -2. I did not realize that time is passing so quickly. I forgot to take row again. That's okay. I'm just going to assume everybody is here today. And then we have one whole week before we meet again. You do have one homework assignment. And then for reading, I'm certainly hoping you guys are going to keep up with the reading, is this entire module. And also the next one, because this one is almost done already. So I want you guys to find some time to try to read injection, surjection, and bijection. Okay, so next week, when we come back on Wednesday, we will finish up just functions, but we'll probably be finishing up, injection, surjection, and bijection too. All right, well, have a nice long break, and because on Monday, you won't be here, so,
Oh, can you upload the chocolate?
right, almost forgot.
Okay.
All right. Actually, I don't need to take roll today because I asked all of you to log in. I can see whether you logged in during this time, so that's good. Unless somebody did not listen and go like, I don't need to log in. Alrighty.
Thank you, Professor.
Mm-hmm.
Were you able to get in contact with some of the old class presidents?
Nope, I have not yet had a chance to do
Okay.
that.
Gotcha. And then
But
also for the quiz, are we only supposed to have one attempt?
um, good question.
Is
I
it so I
cannot
just ran
remember.
through
I
it?
think it's only one attempt.
Okay.
Yep. So
Well,
that means you just have to spend time and make sure that.
I already
Oh, you turned it in already?
Yeah. So
What score did you get?
I got 7 out of 10.
Oh, okay.
I messed up on some of the symbols towards the end bits, so
Well, since I did not remind people it's only that, I can,
okay.
yeah, I'll
And then
give
yeah,
you.
I'm gonna really take my time on that one.
Mhm.
And my friend, unfortunately, is out sick today, so the guy who was in 320 late last time,
Oh, okay.
yeah, he'll probably have a doctor's note.
Okay. Yeah, I think he emailed me already, and I said that, it's
I've been
okay.
trying to call him all day. I guess he just went back to bed.
Oh, so he's that sick, huh?
Well, he has IBS, irritable
Gotcha.
bowel
Yeah,
syndrome.
I understand that.
He's
Yep.
uh he's got like a really unique condition. He actually ended up going to options instead of our high school.
Gotcha.
But
All
he's
right.
a good
Well,
person. So,
I totally get that. Not a problem. In fact, for him, he can consider, basically, just doing this class remotely if he wants to.
yeah.
I can arrange that with the DSPNS, the disabled, student department here.
Okay.
So I can arrange that so that he can do it, remotely whenever he needs to, because I know that it's not predictable. It's not like you can tell
Yeah.
in the morning, not even in the morning, whether you can make it in the afternoon.
Yeah, literally all he does is just he doesn't even drink water while he's at school because
Oh, okay, I
it
see.
can be that bad.
Yeah, but that's not good either.
Yeah.
Not staying hydrated is not good.
Yeah.
Yep. All right, okay. So I'll have a word with him and offer him,
I
an
guess I
option.
should ask for advice on like, should I call it coding club? Because you were like kind of hesitant on me calling it that. The main thing is I didn't want to put it as like competitive coding club or a Godot club or anything like that.
Oh, I
because we
see.
probably wouldn't get that many members, but
I think computer science club is generic and yet it is descriptive. It's not
Okay.
descriptive, it is descriptive. So people know what it is,
so
and
coding is a little more generic.
coding is a little bit too specific.
Okay.
Because as a computer science club, you guys can, have, you can invite like guest speakers to talk about employment at Google. You can talk about, quantum computing. You can talk about
Okay.
a lot of things. But coding is kind of more limited. It's really just one small aspect of computer
Sure.
science.
Did you send out the poster already? Or,
Not yet.
Then I'm probably just gonna get you a new poster on Wednesday.
Okay. All right. Sounds good. Yep.
I was just wondering for the homework. Is it intended that we only give one attempt for?
Yes. Did
Okay.
you submit already?
Oh no, I haven't submitted it. I was just wondering because like.
Yeah. Yep. He already submitted.
Oh.
So I'm going to have to reopen it for him,
Hmm.
just so that he can get a second chance, because I wasn't expecting people to turn it in class.
I was just wondering because like for your last like Well, when I took your 310 class, we usually had like infinite attempts, but
Oh, no,
I
no,
know-
no. This one I gave you, I'm giving you guys a whole week to do it. So don't hurry. Don't try to rush it because that's the whole point. Do not rush it. You really think it through. Make sure you understand the concepts. Yeah.
Okay. Thank
All
you.
right. Mm-hmm.
Have a nice weekend.
Yep. You too.